So today we're just going to really quickly finish section 1.2 and I'll give you homework for that. So far we've learned that you can change a system of linear equations into a matrix, and then you can row reduce that matrix to reduced echelon form, and that should give you the solution for the matrix, for the system of linear equations. So we saw a few examples. Example 1, we have 4, 2, -1, -3, 1, 2, and 1, 3, -5. -10, 0, 17. And we transformed this matrix, or we row reduced it, and we ended up getting 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 4, -2. Okay? And in this example, because we have a pivot in every column, okay, then this tells us one solution. And the solution is x1 equals 1, x2 equals 4, and x3 equals -2. In example 2, we saw the following matrix. We saw 0, 3, 3. And we saw when we transformed this to a reduced echelon form, we got 1, 0, 0, 0, 1, 0, -2, -2, 0, 3, 2, 0, 0, 0, 1. Okay? And in this case, we saw there are only 3 pivots. And here, for these two, we say x3 and x4 are free variables. Okay? And if there exists, this means there exists. If there exists a free variable, then there are infinitely many solutions. And soon we'll learn how to represent those solutions. We can give a formula that will give us all of the solutions, for example. But for now, just know that if you see a case where there exists free variables, and free variables correspond to columns in which there is no pivot. Okay? And if there are free variables, then the system of linear equations has infinitely many solutions. And in another example, if we have a system, let's say, if we have a system and then we row reduce, and when we do that, let's say we get if we get 0, 0, 0, 3, then in this case, okay, in this case, we will have no solution. Okay. So before I move on, I want to talk about the geometric interpretation of a solution, at least let's say for one solution, okay, for a 3 by 3 matrix, or for a system of 3 equations with 3 variables, okay. So we saw when we had 2 equations with 2 variables, for example, 3x plus 2 equals 5, 3x plus 2y equals 5, 2x minus 3y equals negative 4. This is 2 equations with 2 variables, x and y. Okay. We saw that this is just a line in 2 dimensions for y and x. Okay. And this is also just a line. And what it means for them to have a solution is that this line intersects with this line. This right here means one solution. And one solution would correspond to, if I had 1, 0, 0, 1, and this right here, let's say, is 1, this right here is 2, I would have 1, 2 here. Okay? If I had no solution, for example, this would mean I would have 1, 0, 0, 0, 1, 2, let's say, right? This right here gives me no solution. And if I had, for example, a line here and the same line that is on top of it, right? This is infinitely many solutions. And this would correspond to something that looks like this. 1, 0, 0, 0, 0, 2. For example. Okay? So here we can see the geometry of what it means for a system of equations to have one solution, to have no solutions, to have infinitely many solutions. Okay? Very often, especially in this class, to understand mathematics, you have to go from algebra to geometry, and then back to algebra. Okay? They're very intimately connected, algebra and geometry. Alright? So now you may ask, okay, I see this isn't very difficult to understand. If I have 2 equations, 2 variables, I know what it means for there to be one solution, 0 solutions, or infinitely many solutions. But what about when I have a 3 by 3? For example, if I have this right here. What does it mean for this to have for this to have one solution? Actually, if I have this, let's say this is x1, x2, x3, or I can use different variables x, y, z, okay? If I have an equation like x plus y plus z equals 1, what is the shape of this? Well, if you haven't taken Calculus 3 yet, you will, you should just accept that this represents a shape in 3 dimensions, x, y, and z. Okay? And this equation is the equation of a plane in 3 dimensions. So if I have something like this, right? Okay? And a plane is something that looks like this in 3 dimensions. Okay? It's like a piece of paper, but it goes infinitely in each direction. And it's completely flat. It's basically like a line. If you were to take a line, which goes in each direction, right? And then you were to move this line this way and this way infinitely in both directions, you would get a plane. Again, it's like a piece of paper that goes infinitely in each direction. Okay? All right, so we understand that this shape is a plane, or we at least, well, we accept that this shape is a plane for now. And then you may think to yourself, okay, so this is the equation for a plane. This is the equation for another plane. And this is the equation for a third plane. So if in 2 dimensions, a solution represented an intersection between lines, then in 3 dimensions, a solution should represent an intersection between planes. So I can draw a different plane here. And right here, there's a line of intersection right here. Okay? And then if I draw a third plane, I can see that maybe it looks like something like this. And this plane intersects both of these at a single point, actually. So maybe I drew this a little bit off. So right. So this is difficult to draw, actually, and it's difficult to see. However, I'm going to upload a video called Intersection of Planes. And you will see how 3 planes can intersect at a single point, or they can intersect in a line, or they can intersect where the planes are on top of each other. And in each case, or I can have 3 planes that are parallel to each other, and none of them intersect. So I have this plane here, I have this plane here, and I have another plane, let's say. And they are parallel, so they never intersect. This would be 0 solutions. And when I have three planes or two planes intersect in a line, I will have infinitely many solutions. And if they intersect in a plane, also I will have infinitely many solutions. And if they intersect in a single point, that's when I have one solution. So in any dimensions, 3 dimensions, 4 dimensions, 5 dimensions, no matter how many dimensions I have, a system of linear equations can either have only one solution, infinitely many solutions, or 0 solutions. And it's easy to see this in 2 dimensions. It's a little bit more difficult, but also easy to see in 3 dimensions. And I will upload a video, MP4, called Intersection of Planes, so that you can see how 3 planes can intersect in a single point. Okay? And the only other thing I want to point out is that when I have a system of linear equations, let's say in 2 dimensions, and I graph them like this, then you may ask yourself, what are we doing when we row reduce? Geometrically. Geometrically, what are we doing when we take something that looks like this and we change it to something that looks like this, or whatever this number is, A, B. When we take something like this and we change it to something like this, basically we're taking 2 lines like this and we're changing them to the following lines right here. Now if this is A and this is B, then what I'm essentially doing is I'm taking 2 lines and I'm transforming the 2 lines where this is their intersection is, let's say, AB, and by row reducing like this from here to here, I'm taking these lines and I'm changing them. So these lines don't actually represent these numbers. They're different numbers here. But I'm just using this as an illustration. If I were to have a matrix that represents 2 lines like this, right, by reducing to the row reduced echelon form of the matrix, what I'm doing is I'm keeping the intersection the same, but I'm changing the lines into the following lines. So this line will become this line, and then this line may become this line, for example. But I'm not changing the intersection. Okay? And this is what geometrically, this is what we're doing when we're doing row reduction. Okay? And the video that I'm going to upload shows you this process for a 3 by 3 system of linear equations. And after taking my class, after taking this section in spring 2020, one of my students, Bariz, made this video after I explained this concept, and after I explained this concept, she made this video using an open source software. And I will upload this video so that you can see what is happening geometrically when we change from something like this to something like this. Okay? That's exactly what this video is showing. Geometrically, what's happening right here. Right? Because algebra is meaningless without geometry. Okay. So this concludes section 1.2. And I'm going to give you homework for it right now. So the homework for section 1.2 is 1, 2, 7, 12, 15, 17, 18, and 21. One other thing you should know. A system of equations is consistent if it has one solution or infinitely many solutions. So if it has at least one solution, we call it consistent. If it has 0 solutions, we call it inconsistent. Here's your homework. It will be due October 5th. Please contact me on Teams if you have any questions.